Hello everyone, this is the technical part of our project on the Union Stream crossings. Representing the Sea Dogs is Elijah Allen, Grace Balling, Claudia Dambois, John Walden, and myself, Lucas Norman. I will restate the client's requirements. The client has asked us to create solutions to the culverts on Quiggle Road and Mount Pleasant Road from washing out in large flood events. To do this, we will design for a 100-year storm flood event. In addition, we have been asked to create open bottom culverts that will satisfy StreamSmart guidelines and allow fish and wildlife passage underneath the culverts. The hydrological data was gathered from USGS StreamStats. USGS StreamStats is also used as for the United States Army Corps of Engineers for their hydrological investigations, so we deemed it a reliable source. The Quiggle Road culvert was recorded at a flow rate of 653 cubic feet per second, and the Mount Pleasant Road culvert at 680 cubic feet per second. For this for this project, we have been following StreamSmart guidelines, which intend to replicate the natural stream underneath the culvert. When implemented, the culvert should not interfere with the waterway in any way, and the water should flow the same as if the culvert was not implemented. Of course, in the case of a major flood event, the water level will rise, and the water may begin to interact with the sides of the culvert, and that may not be able to consider unimpeded by the culvert. However, a 100-year or smaller flood event may not be considered a natural flow, and thus the StreamSmart guidelines of non-interference do not apply. The substrate implementation is meant to emulate the existing bed of substrate. With time after implementation, the substrate will be washed away, but will be replaced by the existing substrate in the stream and will maintain a natural stream bottom. And of course, the Stream Smart Guidelines allows fish and other wild passage to travel underneath the culvert.
Points for the bankful width were taken from the edge of the stream. The goal was to find points where the ground transitioned from dirt and mud of the stream to grass, suggesting the height that water often reaches in the past. Stream Smart provides guidelines for the bankful width and the width of the culvert you need to design. It must be 1.2 times that of the bankful width. For Quiggle Culvert, this required 23.9 feet, and for Mount Pleasant, it required 23.25 feet of width. So both of our designs revolved around a 24-foot minimum culvert width. Our analysis looked at two Manning's roughness values, 0.03 and 0.04, as both streams flowed straight without deep pools and with some weeds and stones. The main guiding principle for our designs of the culvert and bridge clearance revolved around the area needed to pass 100-year storm events. The process of determining this required area begins from our site survey, where points were taken upstream of the Mount Pleasant culvert. In order to create a cross section, we took 5 points. One on the upper left bankful width location, a second where the water's edge begins on the left, a third from the middle of the stream, and then 2 more at the water's edge and the upper bankful on the right side. This process was done at 2 locations upstream of the Mount Pleasant culvert, 50 feet and 100 feet back from the opening. These cross-sectional points were calculated, and the horizontal distance between these points was used to determine this value. The channel slope was calculated from taking the low point of the nearest cross-section upstream of Mount Pleasant culvert and the low point of the first cross-section after the culvert. Using this, we can create a proper channel slope where the stream would like to flow, and then we can lay our culvert in such a manner. The roughness coefficient used for our designs was the 0.04, since it produced the largest values. The Manning's roughness equation was used in our process to calculate flow values that can be seen based on both upstream cross-section values. The average of this value was used in our design along with the average cross-sectional area, taking the average flow rate, which was 127 cubic feet per second, and dividing it by the average cross section of 33.6 feet squared, we get a flow speed of roughly 3.8 feet per second. Finally, we can take this value along with our 100-year storm event from StreamStats, which was 680 cubic feet per second, and divide that by the velocity we determined to be 3.8, and arrive on a design flow area required for water passage for the culvert and the bridge options of 180 feet squared.
I'm going to take you through our culvert options. We're going to compare the open bottom culvert to the single span bridge. We used a RACI matrix comparing maintenance, cost, environmental impact, sustainability, and appearance. Looking at our bridge, we designed a steel girder bridge with a girder length of 30 feet, with the opening under the bridge to be a width of 24 feet and a height of 10 feet. This cost is $500,000. Looking at the open bottom culvert, we have a precast concrete arch. The span is 24 feet and the length is 32 feet, with a cost of $400,000. Both structure options have minimal maintenance, where every 2 years they have to be inspected, and a possible removal of debris after a big storm. Both structures raise the road grade, which will require a vertical curve that will slope into the existing roadway. Both structures do match the 100-year storm criteria to pass that water through. We recommend an open bottom culvert.
Hello, my name is John Walden, and I'll be talking about the technical aspects of the Mount Pleasant culvert. So, like the Quiggle Road culvert design, concrete was chosen as the material for the culvert at the Mount Pleasant crossing. Concrete was chosen over steel because concrete was found to be a better supporter of large soil pressures bearing down on a culvert. This was an important factor because the design culverts are a lot larger and a lot wider than the culverts that are in place right now on site. This means that there's going to be a lot more soil bearing down on top of these culverts. Concrete was also chosen because for larger sized culverts, concrete is often cheaper than steel. Concrete was chosen over aluminum because the Maine Department of Transportation recommends that aluminum not be used as a material for a culvert. Foundations or the footings of the culverts were designed based on the assumed bearing capacity of the soil within the region and the assumed loading that would be applied on the new culvert. These assumed values are conservative estimates that are based off AASHTO guidelines. The footing width would need to be 9 feet wide on each side of the culvert. Maintenance on the culvert would be minimal. The only thing that would most likely need maintenance after installation would be the surrounding riprap of the structure or the bedding of the culvert if either were to wash out. It would also be important to clear any blockage that could build up within the culvert, as blockage can reduce the total area of flow underneath the culvert. The culvert structure that was selected had a span of 19 feet 11 inches and a height of 10 feet and 6 inches. This was the minimum prefabricated size that could be selected that could still allow for the full flow of a 100-year storm to pass through it. The culvert was designed to be approximately 36 feet long to adequate for the passage under the width of the road.
So now to put everything for the Mount Pleasant Road culvert into one drawing. You can see the existing culvert is in the center of the drawing, which is 5 feet in diameter. The proposed open bottom culvert has a much larger area, which allows water to flow through in case of a storm event. The blue line on the bottom is the normal high water level line, and the blue line above it is the 100-year storm elevation. As you can see, the 100-year storm elevation is above the existing road grade, which is why we needed to raise the road elevation. The stream bed was designed using Stream Smart guidelines, which is to match the existing stream bottom, and we also used our survey data. We designed 9-foot footings for the culvert, which is a conservative design. We also would like to thank you for taking the time to consider our design, and we look forward to your questions on Tuesday. Thank you.